Born in Turin, Italy, Lagrange always considered himself a Frenchman at heart, due to his father's deep French ancestry. Growing up, Lagrange was fascinated by Beccaria's teachings of physics and mathematics, which began his understanding of what would be his future career. Due to Lagrange's poor finances throughout his early life, it was not long before he began his career in mathematics. Many of Lagrange's calculus applied to mechanics. Differential equations, in particular, were applied to fluid mechanics. The Lagrangian description of fluid flow goes to the molecular level, using position and velocity vectors to map the behavior of individual fluid particles, much like the tracking of billiard balls on a pool table. One of Lagrange's biggest contributions, the Lagrange points, can be applied to modern physics today. Lagrange points are a location in space where the combined gravitational forces of two large bodies, such as the Earth and the Sun, equal the centrifugal force felt by a much smaller third body. The Lagrange points, also noted as the so-called three-body problem, consists of 5 points within our solar system. The first 3 are noted as unstable, as there is little to no gravitational balance in this space. One behind the Earth, another between the Earth and the Sun, and a third behind the Sun on the opposite side of where the Earth's position resides. These 3 together form a straight line from behind the Earth to beyond the Sun. Points 1 through 3 are about as balanced as a minecart on the top of a hill. It is impossible to remain stationary. The last 2 points, 4 and 5, are known as Trojan points, that are completely balanced areas in space, almost like a ball in the bottom of a bowl. Entities that fall into points 4 and 5 remain in a restful state. These points lie along Earth's orbit at 60 degrees ahead of and behind Earth, forming an apex of 2 equilateral triangles that have the large masses, Earth and Sun for example, as their vertices. These points have since been identified as possible habitable locations. While Lagrange wasn't the only one to come up with the idea of the three-body problem scenario, his contributions to physics and calculus have been referred to time and time again by mathematicians around the world. Finally, we have Carl Friedrich Gauss, born in modern-day Germany in 1777, was famously known for his clever mind at a young age. At the age of 7, the then elementary school pupil was able to find the sum of all integers from 0 to 100 by spotting that the sum was 50 pairs of numbers that add to 101. Before the age of 20, Gauss single-handedly discovered Bode's law, the binomial theorem, the law of quadratic reciprocity, and the prime number theorem. After receiving stipends from high-ranked officials for his work, Gauss dedicated himself to research. By the early 19th century, Gauss was able to create the first clear expression of complex numbers, as well as the expression of complex variables within functions. While he wasn't the first to express them geometrically or algebraically, his new method popularized their use, and his notation of how we write imaginary numbers is regularly expressed today. For much of Gauss's life, he had also been fascinated with the topic of theoretical astronomy. For many years, he held the post of director of the Astronomical Observatory in Göttingen. When the planetoid Ceres was in the process of being identified in the late 17th century, Gauss made a prediction of its position which varied greatly from the predictions of most other astronomers at the time. When Ceres was finally discovered in 1801, it was almost exactly where Gauss had predicted. This was done using an early application of the least squares method, a method to find a line of best fit for a set of available data. In the world of probability, Gauss was responsible for the creation of the modern-day bell curve, which has been used for countless statistical data representations. This curve is otherwise known as the Gaussian distribution, the Gaussian function, or the Gaussian error curve. This curve has a symmetrical body consisting of a peak value, usually representing a mean, and 2 troughs on either side of the apex, indicating lesser values within the context of the graph. Many of Gauss's findings have heavily influenced modern math and are now staples in the worlds of calculus, physics, and statistics. From linear algebra to astronomical theory, it is clear that we would truly be lost without the knowledge of this individual.